We are on lesson number 5 of Larson. This is actually the first lesson of calculus. What we've done so far is review pre-calculus to get ready to be successful in calculus. We're looking at finding limits graphically and numerically today. So to talk about what that means, they have presented the function here, x to the third minus 1 over x minus 1. This function is undefined when x is equal to 1 because you would be dividing by the number 0, because 1 minus 1 is 0. You can't divide by 0. So looking at it with a graph, as f of x approaches the number 1, there's a hole. And so if you tried to find the actual number of f of 1, it does not exist. But the limit as x approaches the number 1 is actually 3. So as the graph comes close from the left and comes in from the right, it's coming close to the number 3. So that's looking at it graphically. Another way you could do it is numerically. You come close and close to the number 1. So you go from the 1 from the right and from 1 from the left. As it gets closer to the number 1 by plugging in infinitely closer numbers to 1, it approaches that number 3. So that's how you do it numerically. All right, and then on the back, just to do some reading here of what it's supposed to look like. This says the limit as x approaches 1 of f of x equals 3. And I'll read this down here for you. This discussion leads to an informal definition of limit. If f of x becomes arbitrarily close to a single number L, and when they say that L, what they mean is it's approaching some kind of y value. So as it approaches a y value, like above here, it was approaching the y value of 3. So it's approaching a y value. As x approaches c, again, that's an x value. It's some kind of obstacle or hole or something from either side. Then the limit of f of x as x approaches c is L. This limit is written as the limit as x approaches c of f of x equals L. So far in this section, we have estimated limits numerically and graphically. Each of these approaches produces an estimate of the limit. So down here, they chose the 3 ways to do it. You can make a table, so numerically you can do it. You can make a graph and look at it. And the other way is an analytical approach, which we're going to do in the next lesson. But I'm going to cheat a little and show it to you today too. So the analytical approach. All right, so sometimes a limit doesn't exist. For a limit to exist, it has to come into the same number from the left and from the right side of the graph. So this is coming in from the left, your left hand. This is coming in from the right, from the positive direction. From positive infinity coming in from the left, from negative infinity. So this graph, as it comes in from the left, and as it approaches the number 0, as it approaches 0, it gets closer and closer to this number down here. I think it's supposed to be -1. And then as it comes in from the right, it gets close to the number +1. So since the number comes into a different number from the left and from the right, the limit does not exist. So the limit needs to be the same from the left and from the right. To have a limit, the y value approaches the same value from the left and the right. And again, here it approached from the right, the number 1, and from the left it approaches -1. It's not the same number, so no, there's no limit that exists. Here's another example of a reason why it wouldn't exist. This is called boundless. As you approach the number 0 from the let's see, coming in from the right, it's going to positive infinity. It's not approaching an actual number, and as you come in from the left, it's going forever to positive infinity also, so it's boundless. So the limit also does not exist because it's not approaching an actual y value, one specific y value from the left and from the right. Another crazy thing that happens, this is the function, if you probably can't read it very well, it's a famous one in calculus I like to talk about that we're going to, I think, solve with the squeeze theorem. But the limit is the sine of 1 over x. If you graph it, it oscillates between 1 and -1. So it never really approaches one specific number because it oscillates between two different numbers. So that limit also does not exist. So down here they summarize what I just talked about with the three pictures. Common types of behavior associated with non-existence of a limit. Number one, f of x approaches a different number from the right of c than it approaches from the left of c. Remember, c is the x value of like a hole or something, or some kind of crazy point where crazy things are happening, so we want to know what the limit is as it comes to that number. And another reason why is if it increases or decreases without bound. So that was this one here. This was increasing without bound from the left and the right. And again, this was coming in from different numbers. That's number one. It approaches different numbers from the left and the right. And the last one, which we just saw up above, is if f of x oscillates between two fixed values as x approaches c. So it oscillates between 1 and -1. Okay, so my least popular method defining it is plugging in numbers that come closer and closer and closer to that number. I don't enjoy doing that, but we're going to do it here. Let's graph it too, though, for fun. So this is x minus 3 over x squared minus 3 as x approaches 3. Let's look at it as a graph for fun, though, first. So y equals, clear out my junk that's in there. Okay, so y equals parentheses x minus 3 divided by parentheses x squared minus 9 parentheses. And then let me check up. My zoom might have been on trig or something. So zoom standard. Okay, so refreshing and going over some rules here for you. This is x minus 3 over x plus 3 times x minus 3. So notice the x minus 3's cancel out, leaving 1 over x plus 3. So what canceled out made a hole. So there's a hole at x equals 3. What remained makes a vertical asymptote. So there's a vertical asymptote at x equals -3. And while we're on it, let's talk about the horizontal asymptote. So that's the limit as x approaches infinity from the left and the right, and we're going to look at that for infinite limits before we're done with this chapter. But what you want to do is the highest power, x on the top, which was x. The highest power on the bottom was x squared. So that equals 1 over x. So the limit as x goes to infinity of 1 divided by infinity is 0. 1 over infinity is 0. So it's also got a horizontal asymptote at y equals 0. So graphing that, we've got y equals 0, and we've got x equals 0, and we've got, no, not x equals 0, x equals -3. And so then it would look like this. And then finishing up here, going a little overachievement here. If you plug the number 3 into what's left here, you plug it into what's left after you factor it out. So when x is equal to 3, when you plug it into x plus 3, you get 1 over 6. 3 plus 3, 6. So that hole is at 3, 1, 6. So there's the hole right there. All right. So we didn't need to do all of that. All we had to do is come up with the numbers here, plug them into our calculator. So that's nice to do once you've got a graph too, because all you have to do is hit second calculate the value, and at 2.9 it is 0.169. And then second calculate the value again, and now for when it's 2.99, and it's 0.167. And you're going to do that over and over again, and I already got them done for us. So if you plug in the next number, it's also 0.167. This one's 0.167. And then you get 0.166, and this one is 0.169 also. All right, so notice it's approaching from the table. So they told us to do it numerically, so we'll do it from the table. So from the table, the limit as x approaches 3 of f of x is equal to 0.167. Now what I did up here, when I plugged it in, this is called the analytical approach. that we looked at on the other side, choice, oh, here, right here is a, nope, it's on the other side. No, we'll see it here in a second. Oh, here it is. All right, so we had 3 different ways to do it. So we just did it numerically, but I also looked at it graphically. But that technically was the analytical approach that I did, when you factor out what they have in common and then just plug it in. If you factor it out, just plug the number in, that's called the analytical approach. So graphing approach, it was coming close to 0.167. Numerical approach, analytical approach. All right. So the next one, the same idea here. So if you were to graph this one, and again, it's nice to graph it because then you can use the graph to pull the numbers out of it. Again, don't forget parentheses. It's the whole quantity on the top. So cosine, parenthesis, cosine x minus 1, and then divide that by x. And I'm going to change my zoom down here to trig. And when you change it to trig, the tick marks here on the horizontal line count by pi over 2 or 90 degrees. So let's see, we've got, it's counting by 90s. This would be pi over 2, and then pi, 3 pi over 2, and then it ends at 2 pi. So it goes through 0, 0, and around here it looked like it was close to 1, and it comes up at the 4 close to 0 again. So I'm just sketching it. It's not part of the grade on it. Okay, so this one to know the limit as it comes close to 0. So obviously we know it graphically right now. It's 0. But they wanted us to find it analytically. So again, we're going to do that. So second, calculate the value. So I'm going to plug in negative 0.1. And I get 0.050. Doing it again, negative 0.01. You get 0.005, and then we'll cheat and I'll copy them all down here. If you put this, I'll put this one in, it's kind of funny. Second, calculate the value, negative 0.001. You get a super small number. When you get anything with an e like that, it's a very, very small number. That means you've got 1, 2, 3, and then the 5. So that is 5e to the negative 5. That means 5 times 10 to the negative 4. 5e to the negative 4 means 5 times 10 to the negative 4, which would be this number. So that the nearest 3 places, it'd be 0.001. And then it's symmetric on the other side, and you get the same numbers. So from the table, the limit as x approaches 0 of f of x, I'm going to say it approaches 0 because it gets super, super small. So it's 0. And then from the graph, we also saw it was 0. Okay, the next ones are going to go pretty fast. We get to use a graph, which really saves some time, and they even graphed it for us already. So the limit as x approaches 0 here approaches the number 1. Here, the limit as x approaches 1 is x approaches 1. There's 2, 3, 4. The graph is approaching the number 4. And this is a good place to stop and talk for a second. The limit as it comes close to the number 1 approaches the number 4. They didn't ask what f of 1 is. If you did f of 1, it actually equals the number 2 here. So be careful. F of 1 is 2, but the limit as x actually approaches 1 is the number 4. 2 very different things. All right, on the next side, number 30 has all kinds for us to do. All right, so they want to know, first of all, what is f of negative 2? So at negative 2, f, there's no number. It's an asymptote, so that does not exist. And then as it approaches the number negative 2, well, from the left, it's going to negative infinity, and from the right, it's going to positive infinity, so it also does not exist. And then they want to know what f of 0 is. F of 0 is 4. That means when x was equal to 0, When x was 0, y is 4. Then we would like to know the limit as x approaches the number 0. Well, that doesn't exist because as it comes in from the left, it approaches the number 1. As it comes in from the right, it approaches 4. So that one does not exist. And then f of 2, oh, there's got a hole there. So that doesn't exist. And then the limit as x approaches 2. Well, from the left, it comes down here to, I think, 1. And then from the left, it also comes in kind of at 1. So that's a 1. Because from the left and the right, they're both coming in at the same y value of 1. And then f of 4 is that dot right there. So that's 2. And the limit as x approaches 4. Well, from the right, it's going to positive infinity. And from the left, it's also going to positive infinity. So it also does not exist because it's not approaching one specific number. All right, see you for some more about limits.